Let us examine the polygonal masonry of Turkey in greater detail and compare it with masonry from other regions where precise stone fitting was also widely employed. Many blocks used in Turkey have an upward-directed protrusion near the front face. Its function is obvious. It prevents the block from shifting toward the facade, effectively stopping it from sliding out of the wall. The joint profiles near the facade have angles close to rectangular, but they gradually become rounded with depth. This geometry appears to be explained not by aesthetics or ease of manufacture, but by function. Such a shape prevents inward displacement of the block. Curvature of the lateral surfaces is also observed. The rounding of the corners and the form of the side faces bring this masonry closer to Peruvian examples. Thus, in regions with high seismic activity, the same structural problem was addressed, limiting block mobility through curved joints and the protruding element of the lower course. Based on the set of features identified earlier, the masonry of both regions can be classified as polycurve. It is noteworthy that in Egypt, in the granite casing of the Pyramid of Menkaure, strongly upward projecting block areas are also found. The designers employed a similar solution. Even though displacement of the casing was unlikely, the possibility was nevertheless taken into account. In Peru, such upward protrusions are absent. Prevention of forward displacement was achieved through wall inclination. A similar solution is known in Japan. In the remains of Hattusa masonry and in the walls of Alacahoyuk, no such inclination is observed. The apparent tilt of the walls at Yanijikali is more likely the result of later inward block displacement. Thus, the methods used to give blocks a fixed position differed between regions, indicating distinct construction traditions. In Turkey, the key Peruvian principle is not employed, whereby a bedding joint was carved beneath each block in the form of a recess, or a downward locking projection was formed between blocks of the lower course. This method was especially common in facing masonry. In honeycomb-type masonry, fixation is achieved through the inclination of the lower faces. In Turkey, such solutions are largely absent. Downward projections occur rarely, suggesting that builders were familiar with the idea but did not apply it extensively. Bedding joints are mainly observed where blocks meet bedrock, where the recess reliably fixed the block's position. Instead, a feature actively used in Turkey but nearly absent in Peru is the stepped joint in the form of a double L profile. In some cases, the horizontal surfaces of the stepped section were made with a slight inclination, which, like a puzzle piece, locked the block in the horizontal plane. In Peru, such joints appear mainly when adjusting course height to achieve a common horizontal level. In Turkey, however, this type of jointing was used even when blocks had equal height. The fundamental difference is that in the first case, the upper block embraces the corner of the lower one, forming a localized profile, whereas in the second case, a stepped form is created along the entire side surface. In Peru, such solutions are rare and fully analogous examples are absent, excluding modern imitations. This discrepancy is another marker of differing construction traditions. In Peru, the enormous diversity of masonry types and styles makes it unlikely that the absence of such joints reflects the preference of a single craftsman. In Turkey, by contrast, the frequency of these elements varies by site, likely reflecting different building periods and workshops. In Peru, recesses or projections with underlying cavities are regularly found at the bottoms of blocks. Such elements are also known at Hattusa but much less frequently. On rough facade surfaces in Peru, nubs or recesses are almost always present. Exceptions involve blocks lacking surplus quarry volume, for example, at Rumakolka. In Turkey, nubs are rare, but deep lower bevels are common. Such cases have been described as a hidden form of nub, where the entire front part of the block projects. A similar solution is seen at Saksai Huaman in the corner megaliths. However, these correspondences are incomplete. Neither nubs nor deep lower bevels are obligatory features, and therefore full equivalence between the regions cannot be established. A common feature in both regions remains the use of bevels. In Turkey, they are particularly deep and pronounced. Moreover, they are more informative. In Peru, bevels often appear symmetrical, which may suggest they were produced simultaneously from both sides. However, closer examination shows that they differ, a conclusion clearly supported by Turkish examples, where the variation in the shapes of adjacent bevels is obvious. In this case, transferring conclusions between regions is justified by the shared physical basis of stoneworking. The surfaces lack traces of toothed chisels typical of later Iron Age masonry. As on the micrite blocks of Sacsayhuaman, white spots are observed here as well, previously discussed separately. Their distribution coincides. Larger spots occur on rough surfaces and smaller ones closer to the block edges. Their dependence on surface treatment quality rather than environmental factors indicates a technological origin. Such traces are typical of percussive working and are discussed in the literature as white patches. Of interest is not only their origin but also how such traces change over time. Thus, similarities are observed at the level of tool marks, edge treatment, bevels, and the final result, precise curvilinear joints. This indicates common principles of stone processing and fitting. At the same time, the structural reinforcement methods differed. It is here that the uniqueness of Turkey becomes apparent, the depressions on the upper and lower surfaces of blocks. Their number ranges from single examples to several dozen. These depressions were produced by drilling. In limestone, this is feasible using tubular drilling with loose abrasive. Tool wear explains the observed 1-2 mm edge. Similar tubes and drill cores are known from archaeological finds. The function of single holes is clear. Sets of 2 blocks connected by a bronze dowel are known. The use of bronze, despite its value, may have contributed to the later dismantling of structures. The use of dowels significantly strengthened the construction. Holes are also found in bedrock where masonry has already been destroyed, indicating the widespread application of this method. No such examples are known in Peru. This represents another structural difference. There are no traces of tubular drilling there, with a single unclear exception, and all holes have a conical form typical of pecking. This is also reflected in door fastening methods. At Hattusa there are holes likely used for fixing door leaves. Parallels exist in Egypt and India. Near some of them, characteristic arcuate wear traces have survived. In Peru, doors were secured differently, using ropes threaded through special loops. A global difference between the regions lies in masonry types. In Peru, freeform masonry predominates, without strict coursing and with L-shaped joints. In Turkey, by contrast, there is a pronounced tendency toward quadrangular masonry with fixed course heights. Even in the Yanıcıkale Tower, clear courses are visible. The only example of freeform masonry in Turkey is Alakahoyuk. Yet even there the block morphology is fundamentally different due to the predominance of step joints. Honeycomb-type masonry has not been documented in Turkey. In summary, despite a general visual similarity in comparable stone processing and fitting techniques, the methods of block fixation and the stylistics of masonry differ substantially. The differences are so significant that it is impossible to identify not only identical walls, but even sections of masonry with closely matching feature sets. Differences in structural fixation methods, from joint geometry and the role of protrusions to the use of dowels, recesses, inclinations, and step profiles, are systematic rather than accidental. These methods affect the very principle of structural stability and reflect engineering logic formed within specific building traditions. Similarities at the level of stone processing are not accompanied by identity in structural solutions, which points not to the legacy of a single hypothetical antediluvian culture, but to the independent development of different schools of stone construction that solved similar problems through different technical approaches. Thank you for watching. See you next time.